Wagwan, my GCSE science students. In today's video, we're going to be looking at the AQA Chapter 1 Atomic Structure. Okay, it's a full revision video. So let's go. The topics that we're looking at in this video, we're going to be looking at what are atoms, how do we separate mixtures, fractional distillation, and paper chromatography. We're going to be looking at the history of the atom, the structure of the atom, ions, atoms, and isotopes, and electronic structures. Okay, so this is a full revision video for chapter 1 for AQA. All right, let's do this. So the first thing that you need to know in this chapter is what exactly are atoms. Okay, and you can see the definition on screen. All right, so they are small particles and they can only be seen with special microscopes, the electron microscope. Okay, and you can see that atoms is everywhere around us. Everything is made up of atoms. Every single thing that you know, that is made up of atoms. Okay, now elements are substances which is made up of one type of atom only. And when you think of elements, you must think of those substances which are found in the periodic table. And you can see a diagram of the periodic table here. All right. So once you're doing chemistry, you know that you definitely know about the periodic table. So an element is defined as a substance made up of one type of atom only. Okay. So when you're representing elements, an element must always be written, the first letter must always be written with a capital letter. All right, so I see this a lot, all right, where students write small n, small a, or they would write capital N and capital A. Okay, that is wrong. That's very, very important. All right, so oxygen is a capital O, not a small o. Fluorine is a capital F, not a small f. All right, similarly, what you have here, iron, potassium, okay, mercury, Hg. So it's very important why for you to write this in elements in this particular way. Okay, it's very important when you're balancing equation and anything like that. All right, so just remember that, very key information. Now compounds are substances made up of two or more elements which have been bonded together. Okay, and here are some different examples of compounds. All right, so you have water, which is basically an oxygen bonded to two hydrogen atoms. All right, you have something like ammonia, which is nitrogen, which is bonded to two hydrogen atoms. Okay, let's use a different color pen. All right, good, so you can see that better. So these are compounds because they are elements which have been chemically bonded or chemically joined. Okay, so right here you would have a carbon double bonded to oxygen. Don't worry if you don't know why it is a double bond just yet. All right, you can check those in my other videos. All right, now to break these bonds, energy is needed to break those bonds. Okay, so just some key points for you to remember. Now we're going back to the periodic table, right, which we mentioned that in these, when you're writing the elements, ensure that you write capital letter, lowercase letter. Okay, now also in the periodic table, you notice that you see some numbers and you need to know the definition of those numbers. Okay, so the bigger number is always the relative atomic mass. All right, and the smaller number is your atomic number or your proton number. Okay, your relative atomic mass, this bigger number, can also be referred to as your mass number. Okay, there are two different definitions, but they end up being the same number. Okay, so the mass number is the total number of protons plus neutrons. Okay, and we will come to that later. What are protons, what are neutrons? But the relative atomic mass, that number is the average mass of all the beryllium found in the atmosphere. Okay, but don't worry too much about that. We will get back to that later. Okay, so as we mentioned before, the bigger number in this case, right, they're both the same number. So the bigger number, we call that the mass number. Okay, and the mass number is the total number of protons plus neutrons. Okay, good. And then the smaller number, which is your atomic number, that number gives you the total number of protons, or, very important, or it also gives you the electrons. Okay, good. So for example, let's look at some quick example. Lithium 7 and 3, okay? So protons was going to be 3 because that's my atomic number there. My electrons also going to be 3 because that's my atomic number there. Remember, atomic number is protons or electrons. And my neutrons, to work my neutrons out, is going to be 7 take away 3, which is equal to 4. Okay? So to work out the number of neutrons, we always subtract the atomic number from the mass number. Okay, so here are a few other ones to try. All right, so my proton is going to be 12, my electron is going to be 12, and my neutron is going to be 24 minus 12, which is also going to give me 12. Let's look at something like aluminium. Okay, so this is going to be 13, that's going to be 13, and it's going to be 27 take away 13, which is going to be equal to 14. Okay, and let's look at this oxygen, which is 8. Electrons also going to be 8. Okay, so just to be clear. And then to work out the neutrons is going to be 16 take away 8, which is also going to be equal to 8. Okay, so from this slide, make sure that you know how to calculate protons, electrons, and neutrons. Too easy. Okay, now the electrons are placed on shells. Okay, good, and you need to know the rules for how the electrons are placed on shells, okay? So your first shell, which is the innermost shell, so right here, we refer to that as the nucleus of the atom, okay? And then you have your first shell, your second shell, your third shell, okay? And inside the nucleus, you have your protons and you have your neutrons, okay? So the rule is, on the first shell, you can hold a maximum of 2 electrons. On the second shell, you can hold a maximum of 8 electrons, and for GCSE purposes, the third shell can hold a maximum of 8 electrons, okay? And any remainder will go on the fourth shell, okay? So the fourth shell, for GCSE, will not pass the fourth shell. Any remaining electrons goes on the fourth shell, okay? Good. So let's look at this. We just did some calculations. How many electrons does sodium have? Remember, atomic number, smaller number, it means therefore I will have 11 electrons. And just to recap, protons, electrons, neutrons, your neutrons is going to be 23 minus 11, which is going to give me 12. Electrons is going to be 11. Protons is going to be 11. So how many electrons we have here? 11. Okay, good. So putting them on the shell, I have 2 on that first shell. I'm going to have 8 on the next shell. When doing electrons, you can use dots or you can use crosses, okay? The next example, I'll use crosses. So I've used 2 electrons so far. Remember we said that we started off with 11 electrons, okay? So I've used 2 on the first shell. So I'm going to represent that as a 2. Put a dot in between to separate the shells. Then I've used 8 on the next shell. So that gives me a total of 10 so far, which means that 1 electron is remaining. That's going to go on my third shell. So it is 2.8.1. And this is referred to as the electronic configuration. Okay. So if you ask in the exam, what's the electronic configuration of sodium? All right, go to the periodic table. You would see that sodium is 23, 11. So you're going to use this to work it out. So it's going to be 2, 8, 1. Too easy. Okay. Good. Let's move on. Let's look for something like phosphorus. Oh, but before I go there, let's go back to this. So if you notice, we have 1 electron on the outer shell. Okay, this will tell us the group in the periodic table. So this means that it's found in group 1. So if I go to my periodic table here and look for group 1, groups mean that you're going from top going down. Notice that sodium is found here in group 1. Okay, let's see if this works out. And also, we have 3 shells. 1, 2, 3 shells. Therefore, it's going to be found in period 3. Okay, so let's check. This is period 1 going across. That's period 2 going across from left to right. Voila! Period 3. Sodium is found in period 3. Okay, good. So you see there is method to the madness in the periodic table. All right, good. Let's look at something like phosphorus, okay? We have 15 electrons. How many electrons does it have? 15. We always go with the smaller number for the electrons, all right? So this time I'm going to use crosses to do my electrons, okay? So we put 2 on the first shell. Remember the rule, 8 on the next shell. Okay, good. So we started off with 15 electrons, which means that I've used 8 on that one, so I've used a total of 10, which therefore means 5 electrons are now on the outer shell. So that's 2, 4, 6. I've drawn 1 too many. Let's erase that one, and therefore it's going to be 2, 8, 5. Okay, so the electronic configuration, I'm going to just put EC for short. For phosphorus is 285. Good. So let's look at the periodic table. So this is 285, which means that it's going to be found in group 5, period 3. Okay, so group 5, period 3, let's check. All right, have a look at that. Group 5, period, that's 1, period 2, and period 3. That's exactly where you're going to find phosphorus. Too easy, okay? Good. Now, here's another term that you need to know for this chapter, an ion. Now, an ion is an atom or group of atoms, and they have a positive or a negative charge, okay? Now, how is it that they get that positive or negative charge? They get that because they have an incomplete outer shell and they're not stable. Key thing. And they can gain stability by gaining or losing electrons, okay? That's how they become stable. So, an atom that loses electron, and lots of students can't wrap their head around this. One atom that loses electrons, because electrons are negatively charged particles, because they're negative, and if you lose something which is negative, what is left behind becomes a positive ion, and there's a special name for this. We call them cations. Okay, good. So you can just remember that cats, they have pause. Okay, cats have pause, and therefore cations are positive. Okay, positive. Okay, good. So it should be positive, but that's just my way of remembering it, okay? And any atom which gains electron, they form negative ions, all right? And we call these negative ions anions, okay? Anions kind of look like the word onions, just ever so slightly, okay? It looks like the word onions, and onions make you cry, okay? And because onions make you cry, I just remember that means that they're negative, okay? So you have cations which are positive, anions which are negative, okay? Now, we're going to look at how exactly ions are formed. So if we look at something like sodium, which is 281, electronic configuration 281, it doesn't have a full outer shell. So if you have a look at the outer shell here, it's not full, and therefore it is not stable. Okay, now in order to achieve stability, it can do one of two things. Okay, it can go looking for 7 electrons. Okay, so it can go look for 7 electrons, or it can lose 1 electron. Which one do you think it will do? Okay, when it loses that 1 electron, this shell now becomes the new outer shell. Okay, and therefore it's now full and stable. Now, based on energy, it is harder to go and look 7 electrons more than lose 1 electron. It might as well you just give that electron up. All right, and atoms are just like us. They're lazy. Okay, so what that sodium will therefore do? That sodium will therefore lose 1 electron. Because it has lost an electron, I want you to pay close attention to the top here. Because it has lost 1 electron, you didn't lose any protons. Protons are positive. Electrons are negative. Therefore, since I have 11 protons, therefore it's going to be plus 11. I've lost an electron, therefore it's minus 10. Therefore, that's how it ended up with that positive 1 charge. And remember, we said that these are called cations, okay? And now this is a stable particle, which we refer to that particle as an ion, okay? Let's look at another example. All right, think about this. You feel free to pause the video and you can try that. So have a look here. This has no charge. Magnesium has no charge whatsoever because that's equal number of protons and electrons. It now has 2 electrons on the outer shell. not stable, what's it gonna do? It's gonna get rid of those 2 electrons or seek 6 electrons. It is easier to get rid of those 2 electrons because you've now lost those 2 electrons. You now end up with this, and therefore you now have a positive 2 charge. Okay, good. So even though you're losing electron, what is left behind is a positive particle, which is referred to as a cation, which is a type of ion. Okay, let's look at something like fluorine. Okay, so fluorine is found in group 7. Okay, so it has 7 electrons on its outer shell. Okay, 9 electrons, so it's 2.7. All right, not stable. It can either get rid of those 7 electrons or it could just seek to gain 1 electron. Which one is easier? Evidently, it is easier to gain that 1 electron. Because you're now gaining an electron, this now becomes minus 10, but the protons are positive 9. Therefore, you now have a charge of minus 1. And this is called an anion. Okay, good. Let's look at something like sulfur, which is found in group 6. Okay, 286. Again, what's it going to do? Is it going to get rid of those 6 electrons or just seek 2 electrons? And it's going to gain 2 electrons, okay? Because you're now gaining 2 electrons, you now have more electrons than protons. Therefore, you now have a negative 2 charge and it is 2 minus, okay? Still an anion, okay? So hopefully from that you can see how ions are formed because they have no differences in protons and electrons and therefore they have a charge, okay? Good. Let's move on. So let's look at this. So we have 3 different oxygen atoms here, and based on what we've discussed earlier in the video, we should be able to work out the protons, the electrons, and the neutrons for each of these oxygen atom. Okay, that would be too easy. So let's look at this. 8, 8, and then 16 minus 8 to work out neutrons, that's going to be 8. All right, protons are going to be 8, electrons are going to be 8. 17 minus 8, that's going to be equal to 9. All right, and then we're going to have 8, 8, and it's going to be 18 take away 8, which is going to be give me a total of 10 neutrons. Okay, so if you have a look here, you realize that even though they're the same oxygen atom, okay, they have differences in terms of the number of neutrons, okay, and also their mass numbers are different. Look at the mass numbers of each of these, they're different, and there's a special word for these are called isotopes. You need to know the definition for isotopes. So isotopes are atoms of the same element. They have the same atomic number, different mass number because they have differences in the number of neutrons, okay? So here's a definition that you can take down. Same element, right? Same number of protons, but different number of neutrons, okay? Good. All right, let's move on quickly. So now, how is it that the atoms were discovered? And we also need to know about the history of the atom. This is very big for the AQA Science Board. Now, atoms, it was first spoken about by a Greek scientist, okay, Democritus, okay, but that was just in like conversations and things like that. But J.J. Thomson, right, in 1897, he discovered the electrons and he found out that electrons, okay, electrons had a negative charge and they came up with the atomic model, which is referred to as the plum pudding model. Now, in this model, what they describe the atom as is this big positive spherical cloud. Okay, so think about it as this big cloud which has a positive charge, and in that positive charge, you're gonna have your electrons, which are negative, dotted all throughout that structure, much like a plum pudding or a pudding which is raisin. So the electrons are the plums, quote unquote. It is referred to as the plum. So don't mean that they're actually plums, okay? Good. Those would be your plums, and but those are electrons, and then this would be your big positive sphere, okay? However, this model was not right, okay? This model was changed. So this model of the plum pudding model. So that model of the plum pudding model, that model was not right, and it changed to this model here, referred to as a nuclear model. Now, the reason why it was changed to that model was because of some experiments which was carried out by Ernest Rutherford in Manchester. Well, actually, it was carried out by his students, Kurt and Geiger. However, because they were students, it was Ernest Rutherford's work. Okay, now what they did, they fired alpha particles. Now, alpha particles are positive particles. So you're firing, remember what they thought at the time was that atoms were positive, and if you're going to fire positive particles there, it should repel. Okay, it should repel. Okay, that's what we think should happen. It should repel. So they fired alpha particles, which are positive particles, at a thin piece of gold foil, which were only few atoms thick. Now, remember, we said that it should repel. However, that did not happen. Okay? What actually happened was most of the particles went through. Most of the alpha particles went through. Okay? Most of the alpha particles went through. Okay? However, on very few occasions, you had some sort of deflection. Okay? So there was deflection on odd occasion, on few occasions. Okay? Now, if it is that we thought that the atom was a majority positive sphere rather, then most of the time it should be deflected. Now, based on this, we said that no, the atom doesn't look like this. What we think the atom looks like is that the atom is actually made up of a small positive space, looking just like that. So what we're thinking is that it's just a small bit, not the majority of it, just a small bit. And we now think that the atom has a central nucleus. Now, the conclusions are, because most of the alpha particles went through, most of the atom must have been empty space. Also, some of it deflected, or few of it was reflected. It means, therefore, that the nucleus, that small bit, must have been positive. So it must have only happened when this was happening there. But the majority of that alpha particles were going through. So you need to know about that, okay? Good. And this was now called the nuclear model, which replaced the plum pudding model, okay? Good. Now, Niels Bohr then adapted that plum pudding nuclear model. So we thought that the nuclear model was like this, with the electrons dotted around. But if that was the case, then the atoms should collapse. Okay, the atom should collapse because of attraction. Okay, but because the atom wasn't collapsing, Niels Bohr then adapted the nuclear model, and he said that the electrons must be found in shells, the way that we draw it today. Okay, electrons must be found in some sort of shells. Okay, and that came up with the Bohr's model. Okay, that's now the Bohr's model, in which the atom is now in shells. Okay. Now, James Chadwick, he then discovered the neutrons, all right, and he provided evidence to show that there are also neutrons found in the middle, and explained where the added mass was coming from, okay, because they already knew about protons, all right. Good, excellent. Now, that summarizes the history of the atom, okay. Now, another thing in chapter 1 that you need to know about is mixtures, okay. Now, mixtures are substances which are not chemically bonded, okay. So mixtures are substances which are not chemically bonded, and to separate them is quite easier to separate than compounds, okay. So compounds, remember we said things like compounds, water, it is not easy to separate water into something like that. That's difficult, okay, because it's chemically bonded. However, mixtures, it's quite easy to separate because they're not chemically bonded, okay. So the different methods of separating a mixture is through physical methods such as crystallization, chromatography, filtration, simple distillation, and fractional distillation. Okay, so let's look at the different methods now of separation. Now, filtration, we use this to separate an insoluble solid from a liquid, okay? And we use a filter paper. So the filter paper, what it has is it has small holes inside of it, or small pores, which will allow the small pores will allow some substances to pass through, but big substances cannot pass through. Okay? And an example of this is sand and water. So you can separate sand and water through filtration, or anything which is insoluble. Now, how does it work? All right? You need to make sure that you have your filter paper, you have your filter funnel, you have your mixture here, you pour your mixture down. The sand is going to remain behind as your residue, whereas the water is going to pass through as your filtrate. So the filtrate is a substance which passes through. The residue is a substance which remains behind on the filter paper. That is your insoluble substance, okay? Good. So make sure you have an idea how that works as well. Now, another method for separating mixture is distillation, okay? So with distillation, this is used to separate um, substances with different boiling points, with different boiling points, different BP, okay? Now, also, it can be used to separate if you have one substance dissolved in the other, such as like salt and water. So yes, they have different boiling point. Water is at 100 degrees Celsius. Salt has a roughly about 500 degrees Celsius, okay? Very, very hard to boil, all right? Or even higher. So what will happen, you heat first. The water, which has a lower boiling point, will travel here, leaving behind the substance with the lower boiling point, such as your salt, that's going to be left behind, okay, in your round bottom flask. The vapor then travels through the Liebig condenser, all right? On the outside of the Liebig condenser, you have water going in. It's not mixing with the tube here, and water coming out, traveling in opposite direction. And this is going to cool your vapor and condenses your vapor, and that's collected at the end. The bit that's collected at the end, this is called your distillate. Okay, good. All right, so just look at what's happening inside the Liebig condenser. Okay, so inside the Liebig condenser, the vapor is traveling down, but then you have water on the outside. It's like a jacket, okay, which cools a tube which is on the inside, okay, and then you have your cool water exiting, okay. So distillation, right, is used to separate a solvent from solid. So the solvent is the substance that does the dissolving from the solid, and distillation occurs in three main phases. You have evaporation, condensing, and then you collect. Okay, too easy. All right, good. Now, distillation, when the vapor comes off, especially if you're using two liquids of different boiling point, the liquid which is collected at the end is not quite pure. Okay, and to help increase purity, we use fractional distillation. Now, fractional distillation separates two or more miscible liquids, meaning that they mix and they have different boiling points, and the boiling points can be close. So an example of that could be ethanol and water, alcohol and water. So ethanol has a boiling point of 80 degrees Celsius, water have a boiling point of 100 degrees Celsius, roughly 80. I think it's about 78, okay? Approximately 80. Now what will happen is you heat the mixture. When it gets to 80 degrees Celsius, right, or before getting to 80 degrees Celsius, you're going to pass through your fractionating column. Now, what will happen in your fractionating column is repeated evaporation and condensation. Okay, so you're going to have repeated condensation and evaporation. Okay, So it's going to condense, fall back down, evaporate until the vapor with the lowest boiling point, which is the ethanol in this case, gets to the top first. Okay, it goes through the condenser, it is cooled and then collected as the ethanol at 80 degrees. So it's going to be pure ethanol. At some point you will have a mixture of ethanol and water, but at 100 degrees it's just going to be water alone. Okay, so please note the difference between your fractionating column compared to your simple distillation. Okay, now your final method of separating mixture is chromatography. Okay, now chromatography is used to separate inks and dyes. It's a separating mix technique which is used to separate inks and dyes. Now we're going to go through the steps. Now in the first step, you draw the line with pencil, not pen, because pencil is insoluble. Okay, if you use a pen, it is going to smudge on that paper. All right, then your second step is that you're now going to put your spots on the paper. All right, and then you label your different spots. So now you have A, B, C, and D. All of this needs to be done with pencil. Okay, then you then add the paper to your solvent. In this case, our solvent is water. Please note that the baseline is above the liquid. So the baseline above liquid. And because the baseline is above the liquid, it prevents the dyes from being washed away. All right. You then use a paper clip to clip your chromatogram on the splint, which is a piece of wooden stick. Okay, and then you leave it for some time, allow the liquid to travel up the paper. Okay, good. So chromatography is beginning to take place. At the end of that, what will happen, it will look something like this. It will separate into its different components. Now how does that happen? Right, separation happens because you have difference in solubility of the particles inside that dye. Okay, so here it's made up of a mixture of different substances. Each one has a different solubility. So as the solvent travels up the paper, it's going to dissolve the sample. All right, and then as it dissolves the sample, the ones which are most soluble, okay, the soluble particles travel further than the less soluble particles. So this one is the most soluble one. Okay, most soluble, and this one will be the least soluble. Okay, least soluble. Okay, good. So you need to also know that there are two phases. You have the mobile phase. The mobile phase is the liquid, the solvent moving up the paper. It's moving up the paper. And the stationary phase, which is the paper itself. Okay, that's the paper itself. Now what's happening, the both phases are in essence fighting for the components, but the one which the component loves the most will travel the furthest in that one. So this one is most soluble in mobile phase. Okay, most soluble in mobile phase. And that summarizes everything for chapter 1. Okay, please make sure that you share, like, and subscribe. I am out. Too easy.